Before we continue with Biot-Savart law problems, let's check your understanding of the right-hand rule for the direction of a magnetic field around a current-carrying wire. Because we're dealing with 3 dimensions a lot with magnetic fields, let's take a look at the 2 most common ways of drawing current-carrying wires, either in the plane of the page or perpendicular to the plane of the page. So if we're in the plane of the page, like the wire on the left, and I want to know the direction of the magnetic field at point M or at point N or at point P or at point Q, what direction would you tell me? Let's do M first. The current is going to the right, so I put my right thumb in that direction. Where M is located, my fingers curl up and point up out of the plane of the page. So anywhere above the wire, the magnetic field is out of the page. At point M, at point N, at any point towards the top of the page above the wire, the magnetic field points out of the page. Now, if I'm in the plane of the page below the wire, where P and Q are, my fingers on my right hand would be rolling around and pointing down into the page. So at point P, at point Q, at any point in this region below the wire, in the plane of the page, the magnetic field points into the page. Now let's take a look at the situation on the right where my wire runs perpendicular to the plane of the page. And I want to know what's the magnetic field at point M, and maybe over here at N, and over here at P, and over here at Q. I put my right thumb in the direction of the current, and it tells me that the magnetic field curls around counterclockwise, because you have to know already that the magnetic field is going to form a circle around the wire. The question is, which direction does the magnetic field point? I put my thumb in the direction of the current, my fingers point counterclockwise. So if I were to draw a magnetic field line, B would point in the counterclockwise direction. If I'm standing at point P with my magnetic field sensor out, it would point tangent to the magnetic field line. If I was at point M, my magnetic field would point to the left, tangent to the magnetic field line. Because my magnetic field at that point is a larger circle with the magnetic field running counterclockwise. At N, my magnetic field points toward the top of the page. And at Q, it would be tangent to the circle, probably in a direction like that. Let's take a look at this situation. We have 2 current-carrying wires parallel to each other, carrying current in the same direction. How do these wires interact? Do they interact? Do they feel a force from one another? Why would a current-carrying wire feel a force? Well, we know a current-carrying wire in a magnetic field feels a force because of that interaction with the magnetic field. We know that a current-carrying wire fills the space around it with the magnetic field. So if the wire on the left is filling the space around it with a magnetic field, and the wire on the right is a current-carrying wire sitting in a magnetic field, well, it might feel a force because of that. So let's take a look at that situation. The wire on the left is filling the space around it with a magnetic field. I'll draw a circle here because I know it forms a circle around the wire. What direction does the magnetic field point? I put my thumb in the direction of the current, my fingers roll in this direction, counterclockwise. So my magnetic field from wire 1 is filling the space around it. As I move farther away, the circle gets bigger and bigger, and they become more spaced out because the field gets weaker and weaker as we move away from the current carrying wire. But at the location of wire 2, our field would look something like this, where this is the magnetic field, and it would be pointing in the counterclockwise direction. So at the location of wire 2, over here, this is where I'm concerned with the magnetic field. What direction is the magnetic field? Tangent to the field line, or towards the top of the page. That's the magnetic field at the location of wire 2, but due to the current in wire 1. Wire 1 is filling the space around it with a magnetic field. At the location of wire 2, that's the direction it points. So what direction would the force be on wire 2? The force is IL cross B. I is out of the page. B is toward the top of the page. So my thumb, when I do I cross B, points toward the other wire. That's the force wire 1 on 2. The force on 2 due to 1. And if you use the exact same logic but flip the wires, find the magnetic field that I2 is producing at the location of 1, you would get this magnetic field. I cross B would give you a force that points toward the other wire. That's 2 on 1. The force on 1 due to wire 2. Of course, they have to be equal and opposite because it's a Newton's pair. This is an interaction between these two current carrying wires. So if one interacts with the other one with a certain force, it has to be equal and opposite the other way. It's a Newton's pair. Now we want to figure out what that force is. So let's look for the force on wire 2 due to wire 1. Wire 1 acting on wire 2. That's going to be the current in wire 2 times the length of the wire times the magnetic field due to wire 1 at that location. And because they're perpendicular to each other, the cross product just yields a sine of 90 degrees or 1. So there we have it. What is the magnetic field at the location of wire 2 due to wire 1? If these are long infinite wires, we know the result. Mu naught I, which I? I from wire 1, that's the one that's filling the space with the magnetic field, over 2 pi r, where r is the distance between these two wires. Because we have this length in here, the length of the wire that's in the magnetic field, these are infinitely long wires. What we usually do is say, what's the force per unit length on the wire? So I have the force divided by the length is equal to mu naught I1 I2 over 2 pi r. Let's do this problem where we try to find the magnetic field at the origin due to this current carrying wire. Pause the video and try the problem on your own first. Now I'll work through the solution. What's the first thing we're going to do is break this wire up into segments that we can deal with. I'll call this one segment 1, and then this curved section segment 2, and then this straight section over here segment 3. And I know that the magnetic field at the origin is going to be the vector sum of the magnetic field from this segment, segment 1, plus the magnetic field from segment 2, which is that curved section there, plus the magnetic field from section 3, which is this little straight section here. This is vector addition. I add them up vectorially. So let's go ahead and find each one of these. The magnetic field due to segment 1 and let's take a closer look. I'm going to zoom in. So the length of our wire is r. The hypotenuse of this right triangle is r. This angle here is 30 degrees. So the cosine of that angle times the hypotenuse gives us the adjacent side. Now we pick some arbitrary segment of that. We call that ds. A little part of the current carrying wire, ds, points in the same direction as the current. The distance from ds to our point of interest is r, and r hat points in that direction. So let's see what ds cross r hat turns out. It's the magnitude of ds, and I'm just going to use dy in this case since I'm parallel to the y-axis. R hat, the magnitude of r hat is just 1, and then I get the sine of the angle when we put their tails together. That would be this angle right here. But the sine of that angle is the same as the sine of this angle over here. I'll call that theta. The sine of 180 minus x is the same as the sine of x. And the sine of that angle is this distance, r sine 30 degrees, divided by the hypotenuse, which is r. Little r, our variable r. Capital R is a constant. It's the radius of this circular path. It's a constant. Lowercase r is our variable, and it changes as we do our integral. Of course, the sine of 30 degrees is just 1/2, so I can rewrite this and r is going to be, we have a right triangle right there, r is y squared. This is y right here on this side. Y squared plus r over 2 squared y squared plus r over 2 squared square root. We're integrating over the whole length of that wire from 0 to r cosine 30 degrees. Using the integral table, I evaluated the integral, and now we'll plug in the limits and see what we get. There's our magnetic field for segment 1. We just need a direction for this. So if we come back up here, there's two ways we can get the direction. ds cross r hat. ds points toward the top of the page. R hat points toward the origin. ds cross r hat points into the page. The other way we can get the direction is by putting our thumb in the direction of the current. So if we put our thumb in the direction of the current, every place to the right of the current carrying wire has a magnetic field that points into the page. Every place to the left has a magnetic field that comes out of the page. Now let's do the curved segment, B2. Remember, for curved segments, this becomes a very simple integral to evaluate because ds and r hat are perpendicular to each other. So ds cross r hat is just ds, and r is a constant. So I get mu naught I over 4 pi, the integral of ds, and of 1 over r squared. The integral of ds is just my arc length, s, and s is equal to r theta. And what was theta in this case? $90, that's 270 plus 30, 300 degrees. Of course, we have to convert that to radians. This expression only works when theta is in radians. So I get 5/12 mu naught I over r. And what direction? When our thumb is in the direction of the current, any place on the interior of that loop, the magnetic field points into the page, and any place on the exterior, it points out of the page. We have one more, B3. Along this segment, our ds points toward the origin, and our r points toward the origin. So we end up with the sign of 0 degrees in there. Remember, there has to be some perpendicular distance away from the line of current to feel a magnetic field. So this is 0. Now we just have to add them all up. They both point in the same direction. We just add them up, and the magnetic field points into the page.